My goal was to create a model of melodic dictation that could plausibly mirror the phenomenological decision-making process that someone may engage with. I say might because I'm not claiming that what goes on here is manifesting in your brain exactly as the model reads. It's a model, thus an approximation from which to build upon. Now, it's one thing to come up with a model that does well, akin to the black box machine learning algorithms that seem to be quite popular right now, but importantly, this is not that. My model, as opposed to those, is that you can see every single step along the way. It's very much like a cognitive, split-second, choose-your-own-adventure book with very specific goals. In creating this model, I had two main goals. The first was to mirror the decision-making process that someone taking melodic dictation might experience, and the second is, in doing that, account for all theoretical factors that were relevant from both a musical and individual standpoint. For the first step, this means also incorporating that when the model is, quote, working harder, it is reflective of the individual taking the melodic dictation working harder. This goal was inspired by research in cognitive psychology, where mental effort to complete a task, such as determining if two figures are rotations or reflections of one another, directly relates to the amount of time that is needed to complete the task. For example, in this work by Shepard and Metzler, time to figure out that the two figures in panel A are rotations rather than reflections, as seen in panel B, maps linearly to the actual physical space measured in degrees that one would have to mentally rotate in order to come to the correct answer. With my model, I wanted to reflect differences between a student breezing through a dictation contrasted to one scrambling to notate their melody. So with these goals established, I then want to talk about the key assumptions that the model makes, since it is based on cognitive processes as opposed to rule-based metrics that you might find in something like Laerdal and Jackanoff, David Temperley's work, or Lisa Margulis's model of melodic expectation. This model relies on three important theories. The first is the statistical learning hypothesis, the second is the probabilistic prediction hypothesis, and the third is the Hick-Hyman law as paraphrased by David Huron. I'll briefly discuss all three and then how they fit together. So the first is the statistical learning hypothesis, which posits that musical enculturation is a process of implicit statistical learning in which listeners progressively acquire internal models of the statistical and structural regularities present in musical styles to which they are exposed over short and long timescales. Also known as, the more an individual is exposed to musical material, the more they will implicitly understand it. This leads to the corroborating probabilistic prediction hypothesis, which states, while listening to new music, an enculturated listener applies models learned via the statistical learning hypothesis to generate probabilistic predictions that enable them to organize and process their mental representations of music and generate culturally appropriate responses. What I'm citing here is directly lifted from a journal in cognitive psychology, but remember, this is basically just what Leonard Meyer said back in the 1950s if it seems like I'm departing a bit from traditional music theory. Importantly, these mental representations can then be quantified in terms of their information content. In my model, I'm doing this explicitly with Marcus Pearce's idiom model, which is a more complex implementation of a multiple viewpoints framework originally developed by Witten and Conklin. The last assumption is that these measures of expectancy can then be used as proxies for units of memory. There are theoretical grounds for doing this, both from Pearce, who asserts that measures of expectancy can be thought of as sort of measures of data compression, as well as David Huron, who in his 2006 book Sweet Anticipation relates this idea to the Hick-Hyman hypothesis, which he paraphrases as more familiar stimuli will be processed quicker than non-familiar stimuli. So just to recap, the model makes three important assumptions. 1, people learn musical patterns implicitly. 2, These implicitly learned patterns form the basis of prediction and can be quantified. And 3, these quantified measures can be used as proxies of memory. So with that established, now I can go on and talk about the actual model. So my model has 3 governing modules. The first is the prior knowledge, which reflects an individual's long-term memory of music. The second is selective attention, which acts as the sensory buffer that models Karpinski's short-term musical memory. And the third is the transcription and reentry function that allows the model to actually write down what it hears. So just to contextualize, my model shares a fair bit of overlap with the Karpinski model, which should come as no surprise since they are both models of melodic dictation. While Karpinski presents an idealized 4-step model for didactic purposes, the first major difference is that my model attempts to be explanatory and accommodates individual differences by having a module that reflects short and long-term memory. Secondly, I collapse Karpinski's first 2 steps of attention and short-term musical memory into a single module of selective attention. My way of thinking about this is more akin to how Nelson Cowan conceptualizes working memory, which frames working memory, or the window of conscious attention, as a spotlight that illuminates anything in long-term memory. I collapse this musical understanding, his musical understanding and transcription into one step with similar submodules. If this seems a bit convoluted, I'm going to try to explain this with a concrete example.